Separable Differential Equations, Part 2. We're going to do just a couple examples where we solve separable differential equations given an initial condition. In the first example, let's look at the differential equation f prime of x equals f of x, where f of 0 equals 1. Recall that a differential equation is an equation with a derivative in it. And separable means I can separate the variables. Everything with an x on one side, everything with a y on the other side. So what we should do is change our notation. F prime of x we can write as dy dx, and f of x we can write as y. Now some of you might already know the answer, because my differential equation says the derivative equals the function. And you might know the function whose derivative is itself, but let's go ahead and show that by separating our variables as such, and then integrating both sides. Recall that the integral of dy over y is a natural log of y. I'm going to put absolute values. I don't need it here because I have the positive value over here, so I know it's going to be the natural log of regular y, but I'll leave it like that. And then do equals x plus some constant of integration. I'll call it c1. And I'm going to move it up here to the top. And do e to both sides. Recall that we need to do e to the entire side as such. And then using properties of exponents, I get y equals e to the x times e to the c1. Since e is a constant and c1 is a constant, I'm going to just rewrite that as some unknown constant. So I get y equals c times e to the x. But of course now I can plug in my initial condition and get that when y is 1, x is 0, so c is 1, and my solution is y equals e to the x, or 1 times e to the x, which I knew because the derivative of e to the x is itself. Let's look at another example. Y prime minus root yx equals root y times x squared. I will again change notation over here. So y prime I'll write as dy dx. And now let's move the negative root y times x to the right side. And I need to be able to separate the y's and the x's. So it looks like that on the right side I can factor out a square root of y and end up with dy dx equals root y times quantity x plus x squared. And now we can separate the variables. I'll get all my y's on the left side, everything with x's on the right side, giving me dy over root y equals quantity x plus x squared times dx. We will integrate both sides. And remember that dy over y to any power is the power rule, except for dy over y to the first. And that's the natural log. No other times when we have dy over y to a power do we use natural log. We just use the power rule. So think about this one as being y to the negative 1/2. So when I add 1, I get y to the pos 1/2 divided by 1/2, but I will flip and multiply it times 2. And then we can do power rules on the right side. We get x squared over 2 plus x cubed over 3 plus a constant of integration. This looks like a good time to plug in my initial condition. When x equals 0, we get y equals 9, so 2 times the square root of 9, which gives me c equals 6. I have empty space here, so I'll write it as 2 times the square root of y equals x squared over 2 plus x cubed over 3 plus 6. And then I need to get y alone, so I will divide by 2, giving me the square root of y equals x squared over 4 plus x cubed over 6 plus 3. And then we'll square both sides, and we'll square the entire thing at once to get our answer. Y equals quantity, x squared over 4 plus x cubed over 6 plus 3, entire thing squared.